For this investigation, we're going to work on pages 335 to 336, so I'd like you to go ahead and turn to that page in your book, 335, or you can look it up on my website. I have this unit 5 on my website, and you can turn in unit 5 to page 335. And I want you to follow along as we just start by reading the top section, which is an introduction to this investigation, and then we're going to work on the problems. All right, so under square roots and radicals, that title, it says, in your work on problems of insulin decay, you found that some questions required calculation with exponential expressions involving a fractional base and fractional powers. For example, estimating the amount of insulin active in the bloodstream 1.5 minutes after a 10-unit injection required calculating 10 times the quantity 0.95 to the power of 1.5. Among the most useful expressions with fractional exponents are those with the power 1/2. It turns out that 1/2 powers are connected to the square roots that are so useful in geometric calculations like those involving the Pythagorean theorem. For any non-negative number b to the power of 1/2 is equal to the square root of b. Expressions like the square root of b, the square root of 5, and the square root of 9 minus x squared are called radicals. As you work on the following problems, keep this question in mind. How can you use your understanding of properties of exponents to guide your thinking about 1/2 powers, square roots, radical expressions, and rules for operating with them? Let's go ahead and look at number 1. Before we do those problems, I'm going to pause and look at the example that they gave in the reading. B to the power of 1/2 is equal to the square root of b. And what I want you to notice is that this is a square root sign. And right there we have a 2. The root is 2. And on b we have a power of 1. So when you're going from here, where we have a radical, and you're going to change it back so that it has an exponent that is a fraction, what you can do is you can take the power that's here and put the root in the denominator here. So b to the power of 1/2 is equal to the square root of b. All right, now let's proceed to the problems in number 1. And in number 1 it says basically that we're going to use that rule where power to a power you multiply, and we're going to come up with an expression in standard number form where there are no exponents or radicals. So in this case, for number 1, what I did is I went ahead and I wrote it as the square root of 2 because I wanted you to see that in the book what they did is they changed this to 2 to the power of 1/2, and then they're going to put it to a power of 2. So then we can use the rule power to a power you multiply, and we get 2 to the 1/2 power times 2, which I'm going to write as a fraction. I'm going to write the integer 2 as 2 over 1. 2 times 2 is 2. 2 times 2 is 2. We get 2 to the 2nd over 2. And then that is equal to 1. So we just get that is equal to 2. So that whole quantity is equal to 2. Basically, the idea is that these cancel each other out. So a radical, or a square root, and a power of 2 are inverse operations. So they cancel each other out. We've talked about that before. All right, number 1, again, I'm showing you that we're changing the square root of 5 to 5 to the power of 1/2. And then we're taking it to a power of 2. 2 times 1/2, you already saw, is going to give us 2 over 2, which is equal to 1, which means that we are left with just 5. Once again, those cancel, we're left with 5. The next example, we have the square root of 12. It's the same as 12 to the 1/2 power. 2 times 1/2, or 1/2 of 2 is 1, and we get 12 to the 1st, which is just 12. So we get the same idea over and over again. Here, the square root of 2.4, so that's the same as 2.4 to the power of 1/2 to the 2nd power. Power to a power you multiply, and we get 2.4 to the power of 2 over 2, which equals 2.4 to the 1st power, which is just 2.4. All right, now on to 2a. Let's look at the directions here. Write each of the following expressions in an equivalent form using radicals, and then in simplest form without exponents or radicals. So 25 to the 1/2 power is the same as the square root of 25. Or, of course, you don't have to write the root of 2. We can just write it like this. It means the same thing. Square root of 25 is 5 because 5 multiplied by 5 is going to give you 25. And really, when you pull it out of the square root, you write plus or minus 5. Most often, we use the positive value versus the negative value. All right, in the next example, 9 to the 1/2 power is the same as the square root of 9, which is equal to plus or minus 3, because 3 times 3 equals 9, and negative 3 multiplied by negative 3 equals 9. 9/4 to the 1/2 power is equal to the square root of 9/4. And when you take the square root of that, you get plus or minus 3/2, because if you think about it, 3/2 times 3/2, 3 times 3 is 9, 2 times 2 is 4, we get 9/4. So 3/2 is the result of taking the square root of 9/4. Number 2D, 100 to the 1/2 power is equal to the square root of 100, which is equal to plus or minus 10. So in number 4, we're going to be talking about a property that is important for you to know about radicals. And what we want to understand by the end of this is that I can take something like this, that's under a radical, has to be separated by multiplication, and I can separate it into the square root of a multiplied by the square root of b, and it's really very helpful for simplifying radicals. So let's talk about this process. We've already said that the square root is the same thing as taking something to the power of 1/2. So we can make that transition. After that, we've already learned our exponent rules. We've learned that power to a group you distribute. And then from there, now we have a to the power of 1/2 and b to the power of 1/2. So we can change that from having a power of 1/2 to writing it in the form the square root of a and the square root of b. What I'm going to do now is I'm going to write the same reasoning out, but I'm going to use numbers, and we're going to prove that it's true. You can use your calculator to check this work. So let's say that a equals 9, and let's say that b equals, we'll say 16. So we're going to write in here the same thing that is over on the other side, 9 times 16, a times b. And then we're going to say, well, that's equal to 9 times 16 to the power of 1/2. Then we're going to use the rule, power to a group you distribute. So we're going to take it to each piece. We have 9 to the power of 1/2 times 16 to the power of 1/2. And then we're going to go back to how we had it before, where we had a radical. We're going to change it from having a power of 1/2 to being the square root of 9, and now we have the square root of 16. And then I want you to think about this. The square root of 9 is equal to positive or negative 3. And we're just going to go with positive 3 for now. The square root of 16 is equal to positive or negative 4. We're just going to go with positive 4 for now. So the answer is 12. Or we could get a negative 12 depending on what you choose for the square root of 9, 3 or negative 3, and the square root of 16, whether you choose 4 or negative 4. So now I want you to check that work. I want you to go back up here. I want you to multiply 9 times 16. And we get 144. And the square root of 144 is also 12. So they are equivalent. You are allowed to take any set of numbers or variables that are separated by multiplication and then split them up so that they look like this, the square root of a and the square root of b. Our next task is going to be to use that same reasoning to prove that when you have division, you can do the same thing. So let's go ahead and modify the argument. At this point, I'd really like you to stop the video, try to figure this out on your own, and then you can start the video again and I will give you the answer. All right. Hopefully you got something to this effect. Basically, the idea is this. we had square root of a over the square root of b, just like in the last argument. We're going to write out a over b to the power of 1/2 instead of having this square root, because you can replace the square root with a power of 1/2. So then from here, just like the other argument, you're going to go ahead and do power to a group you distribute, and you're going to give the 1/2 power to the numerator and to the denominator. So you have a to the power of 1/2 divided by b to the power of 1/2. From here, we're going to go back to what we had originally, and we're going to, instead of using the power of 1/2, we're going to write these as having a square root symbol. So we have the square root of a over the square root of b. So it's the same idea. Originally, we have the entire quantity a divided by b underneath the square root, and now we split it up into two different quantities. We have a underneath the square root and also have b underneath the square root. And you'll see as we do some more problems that these two models will help us to just simplify problems more easily than we would be able to without the rules. These examples should go in your notebook, and we're going to go ahead and